Cool, so now let's get into 3a. So with 3a, it's super important to see that we're taking in a double, and this is probably pretty different from most methods you've seen because usually they take in integers, and this is going to be really important for our runtime analysis. So the second thing we'll note is if n mod 2 is 0, we're going to go into that for loop and do a whole bunch of extra work. So depending on whether n mod 2 is 0 or not, we're going to be doing a different amount of work. Last thing we notice is we're going to have one recursive call to g of n over 2. We saw earlier that the work we're doing depends on n mod 2. So in our best case, we're never ever going to go into this for loop, and n mod 2 is not going to be 0 for every single call. All right, but in our worst case, n mod 2 is going to be 0 for every single call. Right, so n mod 2 is 0, 1/2 of n mod 2 is 0, 1/4 of n mod 2 is 0, and so on. We can rewrite this as, in our best case, n is not divisible by 2, right? So n is some odd number or some number with a bunch of decimal places. And in our worst case, n is a power of 2. First, let's look at our best case. In our best case, n is not divisible by 2, and we're never ever going to enter the for loop. That tells us that the work done by our node is only in this if statement, right? In this check where we're seeing if n mod 2 is 0. So at every single node, we're doing constant work. And here I have this recursion tree, right? Because we start off with g of n, that's going to make a call to g of n over 2, and then n over 4, and so on until our base case. We saw that at each of these levels, we're only going to be doing constant work because we're never going to enter that for loop. And this is one part where that double, where the information that n is a double is really important, right? Because if n was an int, then n mod 2 could end up being an even number. But in the case of a double, we're never ever going to be able to get an even number from n divided by 2. So now we have the work done per node is theta 1, and that's equal to the work per layer in this case because we have one node per layer. So the work per layer is also theta 1. In order to find the total work, we once again just need to know the number of layers, which ends up being log n because we are dividing by 2 at every step. So the total work done in our best case ends up being theta of log n. So for our worst case, n is going to be a power of 2. And at every node, we're still going to be doing that constant work check to see if n mod 2 is 0, but now we're also going to enter this for loop. In this for loop, we start off with double I equals n over 2. We're going to keep going until I is greater than or equal to n over 4, and at every single step, we're going to have I. That tells us that we're only going to go through this for loop 2 times. The first time when I is n over 2, and the second time when I is n over 4. Every single time that we go through this for loop, we're going to call this function with a linear runtime, and that tells us that the first time we go through, we're going to be doing n over 2 work. The second time, we're going to be doing n over 4 work, and in total, in that for loop, we'll be doing 3n over 4. We can kind of ignore this constant work because the work done by the for loop is so much larger. Here I have that recursion tree again, starting off when our input is n, we're doing 3n over 4 work. Once we have our input, we also have our work, so that ends up being 3n over 8. When our input is n over 4, the work done is 3n over 16. And we can see this pattern carried down until our base case, when our work per layer is 3n over 4 times 1/2 to the power of d, which I will get into a little bit more later. But anyways, to add up our total work, we'll just add up the work at each of these layers. So something really cool to notice is we have this great pattern, right? So at every layer, the work per layer is 3n over 4 times 1/2 to the power of k, where k is the layer that we're on. And you can see at this first layer, we're just doing 3n over 4. At this second layer, which is layer 1, we're doing 3n over 4 times 1/2. And we can sum up all of these layers over here. So here we have 3n over 4, 3n over 8, and so on. And D is our base case layer, right? So D is equal to log n because we're going to have log n layers in this recursion tree where we divide n by 2 every single time. A nice simplification that we can use is 1/2 to the power of d is 1/2 to the power of log n, but that just ends up being 1 over n because 2 to the power of log 2n is n. This is just to make the math look a little bit nicer, but we can take out that 3n over 4. Here you can see that we're having the work, so we start off with 1, then 1/2, then 1/4, and so on. And if we distribute that n, we're getting something that hopefully looks a little bit more familiar, right? So we know that n plus n over 2 plus n over 4 all the way until 1 is going to be theta of n, and overall this runtime is also going to be theta of n. Going through the intuition for this, whenever we have a geometric series where we're having the amount of work we do at every step, we expect the work to be dominated by this top node. So intuitively, we would expect this to be theta n, and this math also checks out. That tells us overall we have best case theta log n, worst case best case theta log n, worst case theta n. And so overall this method is omega log n and O of n, since we can lower bound it by log of n and upper bound it by n.